Okay. Hello, everyone. Welcome to Formula Bharat's Driverless Vehicle Workshop 2023. The topic for today's session is virtual detection of cones, hosted by MathWorks. The topic will be presented by Wang, Student Programs Application Engineer at MathWorks. So, without further ado, let's begin the session. Over to you, Liping.
Thank you. Hello. Hello, everyone. My name is Wang, and I'm a education program engineer at MathWorks. Welcome to this webinar. I have supported the Formula Student China competition since 2019. And during my support to this competition, I found most driverless teams know MATLAB can help them prototype the path planning and also the control algorithms, but do not know that MATLAB can support the whole workflow for perception. This is a picture taken by a Formula student racing car in China. Similar as shown in this picture, in Formula student driverless competition, cones with different colors are usually placed on the two boundaries of the track. For example, here in this track, we have red cones put on the right boundary of the track, whereas green cones on the left boundary of the cones. So cone detection becomes a very necessary and also very important step for a driverless racing car to identify the track and then follow the track. So in this webinar, I will introduce how to do this cone detection use deep learning for Formula student driverless competition. I don't know whether you used the MATLAB before, but in this one, I will show the whole workflow. Like first one, in order to do supervised learning, we need to label the images. In that step, we need to put the bounding box around the object that we want the car to detect, like the cones. And then we design a deep neural network and use the network to train, use the labeled image to train the network. After we got the trained model, we can deploy the model to a GPU. Then use this GPU, the model running in the GPU, to detect the cones of the new videos. So you can see here, these cones are detected with the trained model that we got in the first step. So the whole content divided into three parts. In the first part, I will introduce how to do data labeling. That is, how to put the label the images that put the bounding box around the object that we want the car to detect it. And then the second step is how to design and train a deep network. Then the third step is how to deploy the trained model to hardware, that is GPUs. The first step, label data. In MATLAB, we provide some apps that could be used to do it interactively. We call it ground truth labeler and video labeler. In this example, I will show how to use the video labeler to do the job. Let me open MATLAB. So this is the interface of the MATLAB. You could find all the apps provided in this apps tab. And then you can click on this one to find all the apps provided by MATLAB. Under image processing and the computer vision part, you can find this video labeler. Then you can click on this icon to open the app. Or in MATLAB command window, you could type video labeler to open this app. Oh, my computer is not so, the speed is not, it's slow now, but I will, now the app is open. It's opening now. Okay, so this is the interface of the app. We could import the video here by click on import, add videos. Then we could select the video we want to label. Here the video is loading. It's a very long video, so it takes some time. Okay, now the video is loading. It's finished the loading now. You can drag on this button to go through the video, or you can click on the play button here to watch the video there. Then we want to label the object we want the car to detect in each frame, like the red cones and yellow cones, the green cones. So the first step is we need to add the labels. We click on this button here on the left corner of this part, and then we type the label name as red cones. And we click on OK. You can see the red cones label has been built. Then we can add another type like green cones. Click on OK. Then if we want to label red cones, we can select the red cones and then drag on the object on the cones that we want to label here. If we want to switch to green cones, we could select the first to select the label, and then do the similar kind of thing, like drag the mouse to to build the bounding box around the object. In MathWorks, there are also some famous algorithms like a vehicle detector and a people detector have been provided in the in here that you could use to detect vehicles or people automatically, or you could use point tracker to track the region of interest over a time interval, or you could add your own algorithms by click on add algorithm, create new algorithm. After we have, for example, label all the sections like what I have did in previous in my free time. I'm opening the session that I have done before. It takes some time. In this one, I label about 64 frames of this video. To in each frame, I label all the red cones and the green cones here, so you can check how it looks in each frame. And in some parts, there are yellow cones show that the car should turn right and turn left. So I did it in another session. It's a segment of the whole video, and where the yellow cones are putting should the car should turn left or turn right. You can check what it looks like. You can see here I also add some label like yellow coins left, and show that car should turn left, and yellow coins right, show the car should turn right there. So there are 4 kinds of label: red cone, green cone, yellow cone left, and yellow cone right here. After we have labeled all these frames, we can export the result to a file, or we could export the result to the workspace. In this case, I save the ground truth to a file, like what I have opened the section file there. Okay, so this is about the first part, how to label the data. Then the second part is how to design the deep learning the neural network and how to train the network in MATLAB. In this demo, we will show object detection. Object detection is quite different from image classification. In image classification, like this one, we only need to tell what is in the image, like there's a cat in the image. But in object detection, we not only need to tell what are in the image, like there are cats, dog, duck in the image, but we also need to tell where are these objects. Like we need to put bounding boxes around the object. That is called object detection. Usually two stages are needed in object detection algorithms. The first stage is called region proposal. Is we use a method like a slide window, selective search, or a separate region proposal network to find the region of interest there. Here in this GIF, you can see the method called slide window. And then the second stage is called classification, where we can use traditional feature extraction algorithms like SRFT, HOT, LBP there, or we could use a general convolutional neural network to extract features. Then the second step is classification. We could use traditional machine learning algorithms like SVM, decision tree there, or use a neural network. So usually the object detection algorithm consists of these 2 stages. Famous 2-stage object detection algorithm named as a faster RCNN. It's a kind of single unified network for object detection. In this network, the images go through the convolutional layers to generate a feature map. Then there's a region proposal network could suggest some region of interest, like the green bounding boxes in this picture. Then this region of interest combined with this feature map using this IOR region of interest pooling method to generate a new feature map. Then this these features in this region of interest could go through the classifier to classify what are the objects in this region of interest. Here, this region proposal network, the architecture looks like this. In each sliding point, we could use some anchor boxes as a reference bucket, as a reference bounding boxes for region of interest. Then this pyramid of reference boxes, like this anchor, called anchor boxes, have been used in the regression functions. So this is a kind of 2-stage objective detection, where the region proposal network has been used to find the region of interest. In MATLAB, there are functions called train faster ICN object detector could be used to train a faster ICN object detector detection network. It works very well, even the objects collapse with each other. For example, here these human beings are sitting in the boat, but both the boat and the humans can be detected there. But the processing speed, here this picture shows the processing speed like frames per second the network can process, and the y-axis is the mean average precision. So here you can see that fast ICN can achieve less than 10 frames per second. The processing speed is quite lower for real-time applications. That's why proposed for real-time application. The UNO-V2 network can have different resolutions. Less resolution, higher processing speed. For example, UNO-V2 with resolution 288 multiplied 288 could achieve around could process 19 frames per second. It's quite high for real-time application. So here in Formula Student Driverless computation, we want the car can capture the video dynamically and process these frames in real time. That's why in our demo, we will use UNO-V2 network to do the job. This is the architecture of a UNO-V2 network. So UNO stands for your only look once. It's a kind of one-stage object detection network. So here the input is also an image there with a different resolution. Here in our demo, we choose this one, 416 multiplied 416. It can achieve processing speed around 68 frames per second. So in this network, the first part is a UNO network to generate the feature maps. Then the decoder have been used here to decode the predictions, like to put bounding boxes around the object have been detected. The feature map here directly including the attributes of each anchor boxes. As we said before, different anchor boxes could be used as a reference region of interest for each sliding point. So in UNO network, the feature map including 13 multiplied 13 vectors. Each vector contains 3 attributes of each anchor box. For example, here we have n anchor boxes, and the 3 attributes of each anchor boxes, including the first one is tx, ty, tw, th, which define the anchor box position. The first one gives the origin location of the anchor box, and the third one, tw, is the width of the anchor box, and th is the height of the anchor box. So these 4 variables define the anchor box position. And then P0 predicts the objective score of each anchor box. That is whether this anchor box contain the object. That is the confidential possibility that there's an object in this anchor box. And then the P of PC here, P of classes, predict the class possibility assigned to each anchor box, whether it's a boat or whether it's a people there. In MATLAB, we provide the inbuilt function called estimate anchor boxes to estimate the anchor boxes size from the training data. For example, you can see in the picture left on the left-hand side, the x-axis gives the box area of each anchor boxes, and the y-axis gives the aspect ratio, that is y to height of each anchor boxes. So each anchor boxes can be represented by 1 point in this picture. And then we use these estimate anchor boxes to use clustering algorithm to estimate what's the size of anchor boxes we should use for each slide point. So this clustering method could, for example, here they divide these anchor boxes into 4 clusters. So the average size of each cluster could be used as anchor boxes that we use for every slide point. Then the next step is to design a UNOV2 detection network. Usually, the network consists of 2 parts. This network is the parts used here, UNO network. It's further consists of 2 parts. So the first several parts is a feature extractor network. It could be a pre-trained convolutional network, neural network, or a convolutional neural network trained from scratch. So you could use like a ResNet or other kind of thing here, or you could train the network from scratch by yourself. Then the second part is a detection subnet. It consists of series of convolutional layers, batch normalization layers, and ReLU layers. So here, this batch normalization layer has been used to stabilize training, speed up convergence, and regularize the model. Then it should be followed by, these layers should be followed by 2 special UNOV2 layers. The first one is called UNOV2 transform layer. This layer transforms the raw CNN output into a form required to produce object detection. So it's used to transform. It's said very clearly from its name. And then the output layer defines the anchor box parameters and also implements the loss function used to train the detector. That's why it's called one stage, because the regression, the size of the anchor boxes directly used in the regression loss function there. Then I need to mention that in some cases, the same object may be detected by several bounding boxes, that anchor boxes in this case. So how to decide which is the strongest one or the most reasonable one to describe the object? The long maximal supervision algorithm has been used here to select the most relevant bounding boxes of the same object. In order to do to introduce the algorithm, I need to introduce the concept of IOU. IOU stands for intersection over unit. It's very easy to understand. Here we have 2 bounding boxes, and the IOU defined as the area of overlapping over the area of union. So this IOU is a value between 0 and 1. If these 2 bounding boxes do not overlap with each other, then this IOU equals 0. If these 2 bounding boxes are exactly collapse with each other, then this IOU equals 1. So this IOU gives the overlap degree of two bounding boxes. Then this long max suppression algorithm could be described like this. In the first step, we need to discard any bounding boxes with a probability of objective C value less than a threshold. For example, this threshold could be tunable. For example, if we define as 0.5, which means the possibility of a class less than 0.5 will be discarded. The bounding boxes should be discarded. And then for all the remaining bounding boxes, we first select the one with highest class possibility as the output. That way we remove it from the remaining ones. And then discard all the grade whose IOU with the one we selected is greater or equal than the threshold. Also, this threshold could be tunable too. And there are likely to be why we do this, because if these two bounding boxes, the IOU between them is very high, which means these two bounding boxes are very adjacent to each other, and they may identify the same object. That's why we discard the ones has a high IOU with the highest one. Then we repeat this second step until there's no grade left. So this is a long max suppression algorithm. With this algorithm, we could find the unique bounding box for an object. Okay, let's show how to implement this code in MATLAB. So after step 1, we label the data. We save this ground truth to a file called ground truth. So here we only need to load the ground truth data to the MATLAB, and then we use this object detector trailing data to subtract the trailing data from the ground truth object. We keep the sampling factor as 1, so every frame will be get out from this ground truth object as the trailing data. Let me run this code. Let's see what the data looks like. So here we try to show the first 4 rows of this training data to show how it looks like. I'm running this code session now. It's running. So here you can see the training data, how the training data looks like. As we said before, we have 4 objects of interest. The first one is green cone, red cone, yellow cone left, yellow cone right here. So then the first 4 frames of this video, this gives the picture, the location of these frames. We store these frames in this folder. You can see here, this is a picture of the first frame captured by a racing car in the track. And then this 5 multiply 4 doubles gives, because each bounding box is described by 4 digitals, 4 doubles, double values here, x, y, weight, and height. So width and height. 5 mean in the first frame, we have 5 red green cones labeled, like 1, 2, 3, 4, 5 here. And red cone, 7 red cone has been labeled. And no yellow coin left and no yellow coin right here. Then we shuffle the training data and split the data into 2 data sets. The first is training data sets, another is test data sets. In the third step, we want to build a UNOV2 network. The network should look similar like we have described in the presentation. So first, we define the input size as the size of the image we want the network can be put as the input. So here we select the ones 416 multiply 416 here. The 3 means is the RBG image. The 3 channels are red, blue, and green here. Then we use the image input layer function provided by MathWorks to generate the input layer. Define the filter size as usually commonly used in CNN architecture. We defined as 3 multiply 3 here. Then this is the main step. We define the middle layers for the feature extractor network. What we have done here is similar to other classification models like VGG. We use a series of convolutional layer, batch normalization layer, ReLU layer, and max pooling layer. And like in VGG, we double the number of channels at very pooling step. Like the first uses 16, then 32, then 64, then 128 here. So until this ReLU 4 layer, the feature could be extracted. Then we put the middle layer together with the input layer to generate the layer graph. Then we use these estimate anchor boxes to estimate like 10 of the anchor boxes sizes from the training data. Last step is we use UNOV2 layers to assemble the feature extractor network together with the detector network. Let me run this session. Yeah, I'm not sure if you remember. As I mentioned before, in MathWorks, we have some apps that can help you interactively do some work. For example, in MathWorks, we have this deep network designer. You can open it by using this command line to the type this in the command window, or you could find this one in the apps. This deep should be under machine learning and deep learning. Yeah, deep network designer. Let's click on this one to open this app. The app is open here. So we could use the command line to build the network. Or here we could use the network designer app to build network. Here we could generate a blanky network, or import the network from the workspace, or import some network that have been built by PyTorch or TensorFlow here. Let's use the second one because we already have the network in the workspace. That choose the one with the whole network to see what the network looks like. You can see the network contains about 25 layers, and the first layer is the input layer. and then some the convolutional layer, batch normalization layer, ReLU layer, max pooling layer until ReLU 4 here. This part is feature extraction layers. Then it's it's connected with the convolutional 1 layer. Then some UNO V2 network contain the batch normalization layer, the ReLU layer. This we copied twice, and then the last 2 layer contains this transform layer, UNO V2 transform layer, and UNO V2 output layer. So this is the whole architecture of the layers. We could add more change the architecture by dragging the other layers into the network and do the connection there. Or we could change the parameters in the on the right hand side to change these parameters here. So this is a deep network designer. Or we could use the analyzer, network analyzer app to analyze how many tunable parameters in a deep learning network. We can type analyze network. Then you can find, for example, how many layers in total and how many nameable parameters used in this network, and what are the nameable parameters used in each layer. And also it could be checked if there's warnings or errors in the network. Then the fourth step is to train the network. The first thing is we need to do here is to set the training options. You can find more information about this through this documentation page. I will skip the details of this in this one. And then you can use the train UNO V2 object detector function to train the network through the training data sets with these training options. Here, since I only have single CPU in my machine, I will not do the trainings now, but I give the training results here. So you can see this training takes about 1 hour, and the loss, the mini batch loss decrease when the training proceeds. And then I save the trained model into a UNO V2 cone detector mat file. Here I just load the file to test the model. Let me run this part. Oh, this one didn't run. Oh. Okay, the model have been loaded. So to evaluate performance, we first test this model in the test data set. You can see the model have been tested in the test data set. And we can print the this picture show the recall possibility vs the precision here for each class, each object. And this one shows the false positive per image vs the log average miss rate of each object. Also, we could run the model in a real-time video to see if the coins have been detected successfully. You can see here in most cases, the coins are detected successfully, even in this red cone right, yellow cone right, yellow cone left case. Okay, So I'll stop running the code and let's go back to the presentation. Then the last step is how to deploy the trained model to hardware. In MATLAB, we provide some coder called GPU coder and MATLAB coder, Simulink coder, could help us to generate, automatically generate CUDA and C or C++ code. And then this code could be deployed to hardware like NVIDIA GPUs or Intel CPUs, ARM CPUs. In this model, we use the hardware support package for NVIDIA. It could be support NVIDIA GPUs like Jetson Xavier, Jetson Nano. The GPU board looks like on the right-hand side of this slide. So you may wonder how to find the support package or how to install this support package. You can find this by click on Home and Add-ons. You can click on Get Add-ons. Then here you can search for NVIDIA. Then you can find this MATLAB coder support package for NVIDIA Jetson and NVIDIA driver platforms. You click on these things, then click on install, that the support package will be installed on your computer. So with this support package, we could remotely communicate with the embedded hardware board from MATLAB. And also we can acquire data from support sensors and image devices connected to the board. And we also can analyze and visualize the data or all the image we got in MATLAB, and also log data from support sensors to help fine-tune your algorithm and for earlier prototyping. In this demo, we choose this one, the hardware called NVIDIA Xavier here. And we first connect this Jetson hardware to our host PC and monitor to deploy the model to the Jetson hardware. Then we can remove the whole the box. Then the application, the standalone will run standalone. It's a standalone program. And then in the Formula Student driverless computation, we could further connect this hardware with the camera. So to distinguish, to do cone detection in real time. If we want to know how to set up the environment, you can find more information about this part in this blog. I will open the blog here. So in this blog, we'll show you how to set up the hardware and host the computer. You first need to install the MathWorks products like MATLAB Deep Learning Toolbox, GPU coder, the interface, and these support packages. And also you need to install some third-party libraries like CUDA Toolkit and cuDNN, and also TensorIT, OpenCV libraries. And also you need to set up these environment variables. Then you can use this app to check if your setup is correct or not. In this demo, I will not show how to set up this. I will just show how to implement the standalone application and then how to deploy the application to the hardware. This is the application that we want to deploy to the hardware. So it consists of several parts. So the first one is we use this coder node deep learning network. We we first store this to load this mat file into the hardware. Then we can use this function load deep learning network to load the cone detection model into this variable called the model. Then we use the JSON to access the hardware. Then we create a video reader object and also the displaying object here. Then for the video object, if it has frames, which means not end, then we first read one frame from the object, then use the model.detect to detect if there's cones in that image. As we said in the long maximal supervision algorithm, there's a threshold which we set at 0.5 here. And then if the bounding boxes, if there's any bounding boxes have been detected, we could insert object annotation to the image. Or otherwise, we do nothing, just output the image directly. Then we use image to display the out image in the displaying object. So this is the function we want to deploy to the model. Then the next question is how to deploy it to Elsevier using a MATLAB function. In MATLAB, we use JSON to access to the JSON Elsevier object. So this gives the name of the hardware. Here, Elsevier is the username of this hardware, and MATLAB is the password of this hardware. So after we use this JSON to, we can find it print out some information here, like it starts to checking whether the third-party libraries have been installed successfully, and what's the version of this third-party libraries. And then we could configure the coder object, like we set the GPU configuration as a standalone executable, like exe here, and the generate example main like as a generate code and compile. We not only generate CUDA code, but also compile the code into a standalone application. Then we use the code gen to generate code and also generate a report. Here it's in Chinese. It says that the code generation is successfully. Then we use .run application to run the code with this function in the hardware. We could also use kill application to make the hardware do not run the application there. Since it's very difficult to shoot this process in real time, so I record a video on this process. So here the code in Chinese, but the main commands are the same. So the first thing is we create a JSON object. Then we configure the coder. And also use code gen to generate the CUDA code and compile the code into a standalone application, then run the application. You can see after we click on run, this application run in this GPU separately. So it's not run from MATLAB now, it's run from this hardware. Okay, so as key takeaways of this webinar. In this webinar, I have been introduced how to use ground truth labeler, video labeler to do the data labeling. That is labeling the images of a video. And the second part, I introduced how to design and train a neural network, use MATLAB's in building functions. Like also, you could use deep network designer to do the work. And third part, I introduced how to build and deploy deep network models onto GPUs with the hardware support package and how to install the hardware support package. You can find more information about how to do object detection in MATLAB using this link. And MATLAB not only support UNO v2, but UNO v3 and UNO v4 are also supported. You can find more information about this by click these links. And also you can find more deep learning examples and code generation examples by this web page. Here I just show one more example, like similar. The workflow I have been introduced is a general one. It also could be used for more advanced application, like this instance segmentation. Here, the object not only detected with the bounding box, but it could be separate from in the image level. Okay, then if you want to find more pre-trained models for computer vision, neural, natural language processing, voice processing, and LiDAR data processing, you can find more models in our MATLAB Deep Learning Model Hub there. And please notice that new models are added every month there. Here's Racing Launch resources. If you have any questions that not have been solved in this webinar, you can write us email through racinglaunch@mathworks.com, and you can find more information about these things under Facebook group, Racing Launch group. And there are some student videos and tutorials, and you can, if you need a software, a free software, you can click on student computation to find the link to your computation and apply for lessons there. And more information, more blogs can be found on this blog page. Okay, so my presentation is there. I'll try to see what we have for. What if you have any questions, you can type in the chat box.
Participants, any questions?
If no questions, today's section is over.
Yeah, okay. So we can consider that there are no questions and we can end the session.
Actually, I have one question. Sorry. Am I audible?
Yeah, yes.
Yeah, Wang. So I don't have any basic idea. I have just only about. I have basic idea about this machine learning and AI. So with that, is it easy to work on this object detection, or we need to study something prior before looking on it? What is your suggestion on this?
We have some on-ramp courses, that is interactive courses in our website. It's free, and it takes 1 or 2 hours to finish some of them. You can start with deep learning on-ramp, machine learning on-ramp there. I think, Will, can you type the link for that course in the chat box? It's a very good start. Yeah, it's a very good start to learn the basic concepts there.
Yeah. Okay. Thanks. That's the question. Thank you.
Yeah, and we have put the link, and you can also, Shrikant, you can also reach out to us at Racing Launch at mathworks.com if you have like specific requirements of any resources. If we have, we can definitely send it to you. So I'm sending the email ID in the chat now.
Yeah. Sure. Thanks,
Yeah.
Alexa.
Any more questions?
No, nothing from my side.
Okay. Amogha, do you have any questions? Okay. Okay. So we can conclude that there are no questions. And I would like to thank you for taking the time to deliver the informative presentation, Lipping, and
Thank you.
Veer as well. I would like to thank all the participants for joining us, and yeah, thank you.
Thank you.
Yeah, thank you so much. Thank you.
Thank you all.
Thank you.
Yeah, thanks
Bye-bye.
everyone. Bye-bye.
Bye bye.